moving towards our next lecture, which is circuits and signals. Now we start with semiconductors. So first is solid state technology. The world of wireless communications really began to take off with the development of semiconductor technology. Another name for semiconductor technology is solid state technology. The reason it is called solid state is that semiconductors are a solid material. The other type of technology is tube technology. In tube technology, all the electrical stuff happens in a vacuum. An example of a tube technology is the old vacuum tube found in the television sets of the 60s. Many of those old tubes were in fact RF amplifiers in disguise. In those tubes, the RF signal got bigger while it floated around in a vacuum in the tube. Vacuum-based electrical products are no longer used in RF communications. It is not that the old tubes cannot do what semiconductors can. They can. It is that semiconductors have two really attractive properties that tubes do not. They can be made very small and very cheap. Next is silicon and gallium arsenide. There are two primary semiconductor materials used to manufacture RF components, that is silicon and gallium arsenide. And these are also known as GaAs, gas. In general, gallium arsenide is used for higher frequency applications. If some RF component utilizes GaAs, chances are that silicon did not work at the high frequency of intended use. When given a choice, a RF engineer will choose a silicon device over a gas device because it is less expensive. Next is silicon, germanium and indium phosphide. There are two new materials making their presence felt in the world of RF, and they are silicon germanium SiGe and indium phosphide InP. The driving force behind SiGe is the handheld mobile phone. Until recently, the output power amplifier in a handset was almost always made of gas. But SiGe not only has better linear performance than GaAs, but it is more efficient, and better efficiency translates into longer battery life. Expect to see more and more SiGe components in the next generation of mobile wireless devices, as they can be made about as inexpensively as plain silicon devices. The driving force behind InP is high frequency, specifically performance at millimeter wave frequencies, that is greater than 40 GHz. InP has amongst the best low noise performance of any material today at very high frequencies. InP can also be used to make power amplifiers, of course, at millimeter wave frequencies. High power isn't all that high. Unlike SiGe, however, for the time being, InP is still relatively expensive to manufacture. Next is diodes and transistors. Diodes and transistors are two basic semiconductor building blocks. RF system uses the following diodes and transistors as shown in this table. You can go through this table by yourself. I can explain the primary difference between them. It is how they are fabricated and from what material they are made. All the diodes pretty much do the same thing, but because they are fabricated differently, they have superior electrical performance in different areas. For example, Schottky diodes are fabricated to be fast, while pin diodes are fabricated to handle a lot of power. The same goes for transistors. Most diode types indicated in table can be made of either silicon or GaAs, while the transistors are made of one material or the other, but not both. For example, you can buy a pin diode made from silicon or one made from GaAs. Each has their advantages, but you know the rule of thumb. Silicon is for lower frequencies, GaAs is for higher frequencies. And now with the newer, more exotic materials, you can get diodes made from them also. Transistors are a little trickier. Like diodes, they too can be manufactured from different materials, but unlike diodes, when the material type changes, so does the type of transistor. Next is diodes. Many different components use diodes in the RF world. Three components primarily use diodes, that are switches, mixers, and voltage variable attenuators, that is VVA. The higher RF frequencies are generated in oscillators using gun, tunnel, and impet diodes. The voltage-controlled oscillators use varactor diodes, which are variable diodes. Next is transistors. RF uses transistors from low noise amplifiers to high power amplifiers to switches, attenuators, mixers, oscillators. There are two different ways to fabricate the transistors, that is bipolar junction transistors, also called bipolars, or field effect transistors. This figure shows the representation of circuit of a bipolar and FET transistor. The only difference you need to know about the two structures is that bipolars have junctions in them where the material changes abruptly and FETs do not. Next is HBT transistors. There is a new type of bipolar transistor available today called the heterojunction bipolar transistor, or HBT. Originally, BJT transistors were only made from a single material, usually silicon. However, somewhere discovered that if you make a BJT from more than one material, you can oftentimes improve its performance in some meaningful way, which is HBT. In simplified terms, HBT is just a BJT made from more than one material. So BJT made from silicon is called a BJT, but a BJT made from GaAs is called an HBT. And when material changes, the transistor type also changes. Next is transistor usage. At least one transistor is needed if there is gain. The transistors of one kind or another are used by all solid-state amplifiers. Two or more transistors are required for an amplifier for producing a lot of gain. The MOSFET made from silicon is the lowest frequency transistor. The bipolar transistors and MESFETs are used above 1 GHz. More RF power is produced by bipolar transistors than MESFETs, while a low noise figure is provided by the MESFETs than bipolar. Bipolars are less expensive and produce high power, while GaAs MESFETs are more expensive. Next is HEMT transistors. For super high frequency applications, a new type of transistors are used called HEMT and PHEMT. HEMT transistors are just MESFETs in which layer of some super fast semiconductor material like INP has been added. Next is integrated circuits. Integrated circuit is a circuit in which more than one electrical device is combined onto a single piece of semiconductor. There are many advantages to doing this, including lower cost and smaller size. When more than one electrical device is combined onto a single piece of semiconductor, it is called an integrated circuit. Next is MMIC performance. MMICs have two drawbacks in their performance. First, since they involve the semiconductor manufacturing process, they are very expensive if only a few will be needed. Therefore, MMIC technology is only used when the volume requirement is sufficient enough to justify the initial investment to develop the MMIC. Second, quite often MMICs have worse performance than the same device made out of individual components. Where performance is at a premium, like low noise in a low noise amplifier or high power in a high power amplifier, the devices are made out of individual transistors or diodes. When performance is not as critical and cost is, the devices used are MMICs. So this is all in this lecture. Thanks.